Welcome to Exploring Computing. Today's video is hexadecimal. So we've seen inside the computer everything's done with binary, but it turns out binary is a bit unwieldy. So in addition to the binary number system and of course our own decimal number system, computers often use a hexadecimal number system. In fact, I would say that you're more likely to see hexadecimal when working with computers than binary, just because binary is just really difficult to work with. So in this video, we're going to take a look at how the hexadecimal number system works. Hexadecimal is base 16. We've previously seen that binary is base 2, and therefore we only have two digits 0 and 1. And of course, decimal is base 10, and so we have the 10 digits 0 through 9. And so hexadecimal is going to have 16 digits, but of course we don't have 16 digits. So what we're going to do is we're going to borrow the letters A, B, C, D, E, and F. And when you add that to 0 to 9, you end up with 16 digits. Why do we use hexadecimal? Well, consider this sequence of binary digits here. This particular sequence of bits is actually an add instruction for the MIPS CPU. And treating it as binary is somewhat of a problem. There's a number of issues with looking at this as binary. One, it's really long, and as a consequence, it's pretty unwieldy. I personally find it a little intimidating looking at these long sequences of zeros and ones, but more important, it's error prone working with all these zeros and ones. It's really easy to accidentally mix one of the zeros and the ones, or to just completely skip one of them and realize when you're done that, gee, I was supposed to have 32 bits and I only ended up with 29. I wonder which one I skipped. So we want something that's a little bit more compact. Now we can use the decimal number system. So if one were to work out the equivalent, it turns out this is the equivalent of 21,710,880 in base 10. And that is quite a bit more compact. But moving from binary to decimal is kind of a pain. We've seen how to do it before. Here we're doing it with just 4 bits, but you can imagine doing it with the 32 bits on the previous page is going to be a big mess. And I haven't shown you how to move in the opposite direction from decimal to binary because it turns out it's a real pain. So I personally try and avoid it whenever possible. Here's the problem. Decimal is base 10, and 10 really doesn't have anything to do with 2. There's a number of different number systems that work quite a bit better with binary than the decimal number system does. One of them is octal, and the other one is hexadecimal. And these work much better because octal is base 8, and 2 to the third power is 8, and hexadecimal is base 16, and 2 to the fourth power is 16. And so there's a natural relationship between base 8 and 2 and base 16 and 2 that just isn't there for base 10 and 2. And it turns out that because 16 is 2 to the fourth power, every 4 bits corresponds to a hexadecimal digit. So there's a natural breaking point where you can look at every 4 bits and say, okay, that's a hexadecimal digit, that's a hexadecimal digit, that's a hexadecimal digit. You can't do that at all with decimal. And since we're not really usually working with 4 bits at a time, we're actually working at 8 bits at a time, it turns out that every byte corresponds to a pair of hexadecimal digits. So a lot of times when you're working with hexadecimal, you'll see lots of pairs of hexadecimal digits. We'll see examples of this in a minute. Okay, so here's a 24-bit color from one of our previous lectures. This particular color is cardinal red. This is the official color that Stanford uses for cardinal red. And you can see we've got our binary numbers up top. We've got our decimal equivalents underneath it, although converting from the binary to the decimal numbers is, again, a bit of a pain. And so what I'm going to show you is how to convert from the binary to the hexadecimal. And this is going to turn out to be easier. All right, so we can immediately break down each of these numbers into sets of 4. Each of these sets of 4 here is going to correspond to a hexadecimal digit. And then to start off with, you can just use a table. And so here's a table of all the possible combinations of 4 bits and their hexadecimal equivalents. But as you continue to get better at it, you'll be able to do conversions between the two pretty easily. You can do conversions of 4 bits to decimal without too much trouble, although I do tend to stall out. If I'm in the middle of lecture and I need to do a conversion, you'll see me puzzle over the problem for about a second or two and just stall on lecture. But if I need to do more than 4-bit conversion to decimal, I'm just going to have to whip out a piece of paper. I'm not going to do an 8-bit conversion in my head while everybody's staring at me in lecture. That's just, I'm sure there are other people that are much better at it, but I just can't do it. All right, so we're going to take our little table here, or we can just go with the right-hand digit is our 1s, the next one is our 2s, the next one is our 4s, and the last one's our 8s. So if we follow the 1s, 2, 4, 8, you can see that this number here, 1, 0, 0, 0, this is actually an 8. Or I can look it up on my table here on the right. Okay, so 1, 0, 0, 0 base 2 is 8 base 16. And now let's do a full byte. So this is a byte from our color, 1000, 1100, and immediately this is where it comes in handy compared to decimal. If I were going to do the decimal conversions, I have to go, oh, that's the 1s, that's the 2s, that's the 4s, that's the 8s, that's the 16s, that's the 32s, that's the 64s, that's the 128s. And if the number gets much bigger, 256, 512, 1024, trying to remember which place goes with what gets really messy. But with hexadecimal, I don't do that. I just split this thing in half. I say, I just want sets of 4 bits. So I say, I've got 2 sets of 4 bits, one set on the left, one set on the right. The set on the left we already did, but you can do it really easy in your head. 1, 2, 4, 8. Remember, each of the places is 1s, the 2s, the 4s, and the 8s. And so we can see immediately we have an 8 on the left. On the right, we've got 1, 2, 4, 8. And that's 12 in decimal. And again, that seems pretty easy. You're like, why don't we just use decimal? The problem is that only the decimal conversion only works quickly if we have small numbers of bits. The hexadecimal conversion always works quickly because we never have more than 4 bits because we can always break the binary number into sets of 4 bits. All right, so we can look this up in our table, or we can do it in our head, and we can see that this corresponds to a C. And so we can see that this particular bit sequence, we've converted the first 4 bits to 8 and the second 4 bits to C. And so combined together, we can see that this whole sequence is 8C. Let's do another one. And so this is another one of the components of our cardinal red color. And I take the bits and I immediately break them into sets of 4. And I can see I have 2 sets of 4. The set on the left is super, super easy because that's clearly a 1. And the set on the right, we have our 1s, our 2s, and our 4s. And so I can see that's a 5. And so I can see that this converts to 1, 5. And in fact, here's the full color sequence here. The amount of red is 8C, the amount of green is 1, 5, and the amount of blue is 1, 5. And this is actually how it's commonly going to be represented. And so what we see here is the official color guide from Stanford. And you can see they've got a bunch of different possible representations of this, including, remember, we've got the RGB, that's our additive color, red, green, and blue. And then we have our subtractive color for printing, that's our CMYK, cyan, magenta, yellow, and key or black. And you can see down at the bottom, they have the hex, and they have the hex listing, which is what we originally converted this to. They have that hex listing there because that's what the World Wide Web uses. And then this is the color selector in Photoshop. Photoshop has a web color setting, and you can see that the web color setting, again, uses these hexadecimal digits. So the point is, if you're going to be doing art, particularly art for the web, you should be familiar with hexadecimal numbers. These hexadecimal numbers are going to show up in lots of other places as well. When we're looking at addresses on the network, we'll see that hexadecimal digits show up on network physical addresses. These are the addresses associated with your device that you have to tell Stanford when you go ahead and register your computer with Stanford, so it will let you on the network. Hexadecimal numbers are commonly used when identifying individual bits in computer memory. And another place you may see hexadecimal numbers is when you see error messages. When the computer crashes, you will often see hexadecimal. Not super helpful, but you'll recognize, you'll be like, oh, that's great, my computer crashed on me. Oh, and hey, look, a hexadecimal number. I learned that in my computer science class. You could tell you're looking at hexadecimal when you're looking at something that kind of looks like a number, but in addition to the digits 0 through 9, you have A, B, C, D, E, and F mixed in. So you can see on the bottom right there, I have what looks kind of like a bunch of numbers, but I also have those F's and A's in there. And so once you get trained for this, you'll immediately look at that and say, oh, that must be hexadecimal. In addition, though, it turns out that there's a convention that's sometimes used, not always, but when we're working with computers, often if a number is preceded by a single zero, that indicates that we're actually looking at a octal number. And octal is used because octal is base 8, and 8 is a power of 2. And so I think it was used quite a bit for a while, but we mostly moved to hexadecimal. But if you see something with a 0 followed by a bunch of digits, that's an octal number. And if you see something started with a 0x, as we see in our computer memory here, that's representing a hexadecimal number. So you look at this little sequence here. If we just see a 12 by itself, that's probably base 10. If we see 0, 1, 2, that's a 1, 2 in base 8. And if we see a 0x, 1, 2, that's a 1, 2 in base 16. All right, that's it for our little introduction to hexadecimal, but you will be seeing hexadecimal throughout the quarter.